Hi everyone. As always, we start with the learning objectives. Today there's going to be two different parts to this video. In the first part, we're going to talk about oscillations, and oscillations are something that you didn't do in the HSCSE, but basically it's a particle that moves back and forth, and that's an oscillation. Then later on, we're going to use what we learned about oscillations to describe waves. And this we have done in the IGCSE, so I will be pretty fast with it because you should be already familiar with all these concepts like wavelengths, frequency, and so on. So we're going to review this, place it in the context of oscillations, and then make it a little bit more formal because we're not in the IGCSE anymore. So an oscillation, as I just told you, is basically a particle that's moving back and forth. Now there's always an equilibrium position, which is, for example, this. So imagine that the ball really wants to be here. But I go and I just displace it here. Now there's always a force that's pulling the ball towards the equilibrium position, so that when I displace it up to here, the ball will move back towards it. But when it reaches this place, it's already moving with a certain speed, so it's not going to stop. It's just going to keep moving, and then the force is going to keep pulling it back to the equilibrium position, so that this goes back and forth and back and forth and back and forth. Now there's many types of oscillations. So for example, I could have a force where this thing progressively loses energy in just something like this, right? Could be that it always takes the same time to do this. It could be that it goes slower and slower and slower. But as long as this thing just keeps going back and forth, that's just an oscillation. However, we are not interested in oscillations in general, but we're going to be interested in a very specific type of oscillation, which is called simple harmonic motion, that we're going to consider in the next slide. But the basic idea is that an oscillation just means that I have a particle, it goes back and forth, back and forth, back and forth. I don't really care how it goes back and forth, as long as it keeps going back and forth, and there's some kind of equilibrium position here in the middle. Now, there's a reason why oscillations are very, very important. So almost everything oscillates. So for example, a plane that's in the sky, there's a turbulence, the wings will perform oscillations. Like pretty much everything you can think of. So for example, if I have a bowl and I put a marble in it and I let it go down, then the marble's going to do this, right? That's another oscillation. So there's many instances of oscillations, and oscillations are very important because I can use them to measure time. So for example, I have a marble here and I have a bowl and I just let it swing, and I count how many times it swings, and that's a measure of time. And in fact, all of our measures of time are based on some type of oscillation. For example, originally, our measure of time was based on the swings of a pendulum. It went back and forth and back and forth and back and forth. So you just counted how many times the pendulum had swung, and then you had a unit of time. Nowadays, the way that our watches work is by counting oscillations in electronic circuits, or atomic clocks count oscillations in atoms. But it's the idea of oscillations, of something that repeats itself over and over again, that allows us to measure time. Without oscillations, we would not be able to measure time, or maybe we would, but it would be extremely difficult. Now, the kind of oscillations that we're interested in are called simple harmonic motion. And the idea of simple harmonic motion is that I have something that's bouncing between 2 points, and these 2 points never change. And not only this, but each oscillation takes exactly the same time. So this takes always the same time to go from one place to the other. Now, in order to define simple harmonic motion more precisely, we're going to start to have to start using mathematics. So the first thing that I want to define is something called the amplitude, and the amplitude is just this distance here. A for amplitude. And of course, it's measured in meters, right? Because it's a distance. So the amplitude of the movement is the distance between, the equilibrium position and the extreme. Bear in mind that it's from the middle to the top, not from here to here. So from the middle to the top, that's called the amplitude. Now, apart from this, there's another very important concept, which is the period. And the period is just how long it takes for this thing to go back to its initial position. So if it's here, just this time is a period. If it starts here, this is half a period, and then this is a whole period, because it's the time for a complete oscillation. So 1 period, 2 periods, and so on. So let's write that down. We have the period that we call t, big T, because small t is time. And the period is, of course, measured in seconds, because it's a time, right? It's the time that it takes for this thing to go back and forth. So basically what I'm saying to you is that in simple harmonic motion, both the amplitude and the period are always the same. Not only this, in simple harmonic motion, actually the period does not depend on the amplitude, which means that if I start swinging this from, okay, so if I start swinging this from here instead of here, the thing will still take the same amount of time to go back and forth. And if I do it from here, again, it will also take the same amount of time. And if I do it from here, it will still take the same amount of time. So no matter where I start swinging this thing from, the period will always be the same. Now, there is a related quantity to the period that I'm sure you are familiar with, and it's called the frequency. And the frequency just tells me how often this thing makes an oscillation. So imagine that the period is 2 seconds. How often does this thing do an oscillation? Well, half per second, right? If this is 2 seconds, then it makes half an oscillation per second. If it takes 0.5 seconds, then it makes 2 oscillations per second. So you can see that the frequency and the period are inverses of each other. So the frequency will always be 1 over the period. And because it's 1 over the period, its units, and remember that this means units, will be seconds to the minus 1, because we're too lazy to say seconds to the minus 1, we're going to call this hertz. So a hertz is just 1 oscillation per second. So the frequency tells us how many oscillations per second, and all we need to do to obtain the frequency is divide 1 by the period. Now, mathematically, it is possible to define simple harmonic motion in a much more straightforward way. So I'm going to remove all this. And the typical example of harmonic motion is a spring. So I have a spring here with a little mass attached to it. And then what I do is I stretch the spring, and then the mass is going to be pulled this way, and then when it compresses the spring, then it's going to be pushed, and then so on. And it's going to describe a simple harmonic motion as long as there's no air and there's ice under, so that there's no friction. So this thing is not going to change, so the amplitude is going to keep constant, and the period is going to keep constant. Now what happens here is that, remember that the force that a spring does is proportional to the displacement, but it always goes in the opposite direction. So imagine that I displace this little mass, certain displacement x, this way. Now this x is positive, right? Because remember that positive is to the right and negative is to the left. So when I displace this thing to the right, here's my new mass. The displacement is positive, but the force is actually pointing this way, right? Because it's trying to compress the spring. So the force is pointing towards the left, which is negative. So the displacement is positive, but the force is negative. In the same sense, when this thing goes over here, now there's zero force because in the end it's in the equilibrium position, but it's already accelerated, so it's going to continue to go this way. And then when the displacement goes this way, now the displacement is negative. But then what happens to the force? Well, now the force is pushing this that way. So the force goes to the right, which means that the force is positive. So you can see that when the displacement is positive, the force is negative. When the displacement is negative, then the force is positive. Now there's a really easy way to express this mathematically, which is that the force equals minus some constant times x, which is Hooke's law that we already know. It turns out that this is the defining characteristic of harmonic motion. However, we normally don't like to talk about the force, and we can just rewrite this in terms of acceleration, right? So we know that force equals mass times acceleration, so mass times acceleration equals minus k times x, which means that the acceleration is minus some constant k over m times x. So again, I can re-express this saying that I will have simple harmonic motion as long as the acceleration is proportional to negative x. And careful, proportional means proportional, not proportional to the square or to the square root. Then that's not simple harmonic motion anymore. It's only simple harmonic motion when the acceleration is directly proportional to x. So if I double x, then the acceleration doubles. If I quadruple x, then the acceleration quadruples. That's the only thing that defines simple harmonic motion. All the other things that I've told you before about the period and so on, these are consequences of this. So again, if the acceleration is directly proportional to negative x, then I have simple harmonic motion. Otherwise, I may have an oscillation, but I don't have simple harmonic motion. So let's plot this. How will this look? So imagine that I decide to plot this thing, and I put the acceleration in the y-axis and the displacement in the x-axis. Well, now when the displacement is positive, the acceleration is going to be negative. So I will have a point here. When displacement is 0, then the acceleration also has to be 0, because something times 0, that's 0. So, and then when the displacement is negative, then the acceleration will be positive. So basically I have a line that has to be straight, because remember, this is directly proportional and should go through 0, but I can't draw. So I will have a straight line that goes through 0, and just like that. And this is the typical graph for simple harmonic motion, if the acceleration and the displacement are proportional to each other, but when this is positive, this is negative. Now, the next thing that I would like to think about is how a position time graph would look for this thing. So let me just, make this smaller. So I want to know how the position, how the displacement is going to vary with time. So this is my displacement, this is my time. Now let's imagine that I start with a certain displacement. So here's my spring, and I'm going to put it vertically so that it's easier to see what's going on. So here's my spring, and let's say that here's my equilibrium point, and I start by displacing it until here. So the first thing that's going to happen is that, well, of course I have a point here, and then as I let it go, this thing is going to go down, cross 0, then further down until it stops, then start accelerating up because it's being pushed, and it's just going to keep oscillating back and forth and back and forth and back and forth. Now if I do this with time, as time goes by, this will do something like this, right? So we will get a graph that looks a little bit like that. So let's draw that. So up and down and up and down and up. Now, does this look familiar? Does this kind of graph look familiar? If it does, pause the video and tell me which kind of graph it is. Okay, hopefully, you told me that this is actually a cosine function of time, because the cosine of 0 is 1, and then this thing oscillates like that. And that's what actually happens. The graph of displacement against time in an oscillating motion is a cosine graph with time. Now if we did speed, things would be very, very similar, but not exactly. So I'm going to leave this here, and then let me just move this. Okay, so now let's say that I want to know the speed against time. Well, now remember that the speed is the gradient of the displacement time graph. So I look at the gradient here, and here the thing is flat, which means that the gradient is 0 here, so the initial speed of this thing is 0. And then here the speed gets bigger and bigger but negative, so I would expect this to go further down and down until here it's the maximum speed, and then it starts to decrease and become 0 again. So it starts at 0, gets more and more negative, then reaches a maximum here, then starts to decrease again, well, decrease negatively, so it's really increased, until it reaches 0. Then after this 0, then the slope gets bigger and bigger, so until it reaches a maximum here, so up, and then goes back down, and so on. So I will get something very similar to what I had before. So I will also get a sine or cosine function. In this case, this is minus sine. And you see, because this is like a sine of 0 is 0, but it should do this, actually does this. So it's like a sine but negative, so minus sine. And I could do the same thing for the acceleration. But there's no need for me to do the same thing for the acceleration, because if I look at this thing, I know that the acceleration, remember, has to be proportional to minus something times the displacement, right? Therefore, if the displacement is positive, then the acceleration is negative. So if I plot the acceleration in the same graph, let's just imagine that I have some different units, it's going to be the mirror image of my displacement. It's going to be something like this. So when my displacement is maximum, my acceleration is minimum, and vice versa. And when my displacement is zero, my acceleration is also zero. Now, it's only harmonic motion if these graphs have this shape. And these graphs will only have this shape if the acceleration is proportional to the displacement. Which means that if I have this kind of graph, so imagine that acceleration here, displacement here, and instead of being proportional, there's some weird shape like this. This is not simple harmonic motion. This is also going to oscillate, and it's going to do something very similar to what we have above, but it's not going to be a simple harmonic motion because the functions will not be sines and cosines. They will have a different shape. So the thing, yes, will go up and down, but it will go up and down in bizarre ways that are not sines and cosines. Because sines and cosines are simple to analyze, that's why it's a simple harmonic motion. This is not a simple harmonic motion. You can call it complex harmonic motion, or you can just call it an oscillation, but it's not simple, because this is not a straight line. Now, the reason we're doing simple harmonic motion is to understand waves, so we haven't been very precise. And now I'm forced to explain a concept to you called phase difference that you will only be able to really understand when we do circular motion. So now you're just going to have to believe me for what this is. Imagine that I have simple harmonic motion doing something like this, okay? And the period of the motion is the time that it takes for the thing to repeat itself. So this much, period. This is time, this is displacement. Now I can ask myself how different 2 points in time are. And this is actually related to an angle, because this is a sine or cosine function. And remember that the arguments of a sine and cosine functions are angle, right? So sine is sine of theta, right? So whatever's inside the sine is really an angle. So I can ask myself, what is the difference in angle between these 2 points, for example? Well, this is actually much easier than it looks to figure out, but I'm not going to prove this to you simply because I think that when we do circular motion, it will make a lot more sense. And this way we won't waste a lot of time on this now. So imagine that here's the difference in time between these 2 points, so between here and here. So what I do is I measure it in my graph, and I get this little t. So let's call this little t. Now, the difference in angle between these two things that I'm going to call theta, I think that's phi. So phase difference is equal to little t divided by big T times 360. And this is something that you just need to know. The justification is very simple. How long in angle does it take for an oscillation to repeat itself? Well, 360 degrees. So between here and here, there has to be 360 degrees. So this is just a simple proportionality, right? If this from here to here is 160 degrees, then from here to here, how much is it? Well, it's going to be the proportion between these two times 360 degrees. So basically, this is really the difference in angle. If you think that this doesn't make much sense, don't worry about it too much right now. This is related to circular motion, which we haven't done yet. All you need to know is that the phase difference is calculated like this. Okay, now we need to consider energy changes in simple harmonic motion. So remember that we have this little spring, and we also can always consider a spring because whatever applies to a spring applies to every single simple harmonic motion. So here I have my spring, and I can displace it this way, and then it starts moving this way. So as it moves faster and faster, this thing will get some kinetic energy. And remember that as it moves further and further, this thing will get potential energy because the potential energy of the spring is 1/2 of kx squared. Now, because there's no friction and no resistance, there are no energy losses. So what I would like you to do now is think about this. So here I have a graph. This is the total energy, and this is the displacement. How do you think this is going to look? Pause the video and tell me. Right, hopefully you realize that since there's no energy loss, the total energy has to always be the same. So, always the same. Of course, the thing doesn't move further away than some certain displacement, so there's nothing here, but everywhere else, that this is always the same. Because it doesn't matter how it's moving, it's not losing any energy. So what's changing really is the potential energy and the kinetic energy, but nothing else. Now let's take a look at the potential energy. Well, because there's this kx squared, this has to be a parabola. Where will the potential energy be maximum? Well, of course, when it's totally displaced from the equilibrium. So at the maximum displacement point, which is at the amplitude. So the maximum potential energy has to be max 1/2 of k a squared, where a is the amplitude. What's the minimum that we could possibly have? Well, of course, that's when x equals 0, and then that's just 0. So here, the potential energy will be 0, and here it will be maximum. Will there be any kinetic energy at the very extreme? Pause the video and tell me. And hopefully you realize that no, at the extreme v is 0, so the kinetic energy is 0 when this thing just stops before it starts accelerating again. So at the very extremes, at the amplitude, the kinetic energy has to be 0. So if I was to plot the potential energy, I would get something like this. I'm going to do it in white. Here it's going to be 0, here it's a maximum, and because this is x squared, there is going to be a parabola shape. So it will do something like this. Now for the kinetic energy, I could be considering the velocity and whatnot, but there's no need. Because what's going to be the maximum kinetic energy? Well, equal to the maximum potential energy, because energy is not lost. So here, kinetic energy has to be maximum and equal to the maximum value of this. So here, that's kinetic energy maximum. And at the extremes, we already agreed that it was 0, because otherwise this wouldn't be maximum. So at the extremes, it has to be 0. In fact, its shape has to be exactly the opposite of the potential energy curve, so that the addition of these two things always gives us the total energy, which never changes. Okay. Now after this long discussion about simple harmonic motion, we can finally start speaking about waves. Now remember that a wave is something, so imagine that I have a string here, and I give it a little twist up and down, and then this little thing called a pulse, so this is a pulse, is going to start traveling in a certain direction. So if my twist was here, then this thing will travel this way. And even though there is movement, because of course this thing is moving up and down, overall there is no general movement of matter. All that's being transferred this way is energy and momentum. So a wave is really a perturbation in the medium that transfers energy and momentum, but not mass. Now, of course, the direction of propagation of the wave is the direction of propagation of the energy and momentum. So if this thing goes this way, that's where the wave is going. That's the direction of the wave. Now, this is from the IGCSE, so I'm going to be very, very fast with this, but remember that there were two types of waves, transverse and longitudinal. In transverse waves, the direction of propagation of the wave is perpendicular to the motion. So in this case, the motion goes this way, but the propagation is going up and down, right? You see that this pulse goes up and down? So in this case, this and these things are perpendicular. So this goes this way, the motion goes this way. And we call this a transverse wave. Transverse. However, there's some waves where the motion and the propagation are parallel to each other. So for example, imagine that I have a little slinky, and this slinky is more compressed in some places, less in others. I don't know if you can see that, but it is that here the slinky is more compressed and here is less compressed. So this thing here, the little slinky wire, is actually traveling back and forth, and so is the wave. So the wave is going this way, and my slinky wires are going also back and forth. So in this case, I have the direction of propagation and the perturbation in the same direction, and these are called longitudinal waves. Now, typical examples of longitudinal waves are sound, and that's pretty much it. sound. Transverse waves, there's plenty. So for example, this one in a string, in a link, if I do it like that, and the ones that we're going to talk about right now are light waves. Now, I will not go very deep into this because, again, when we do electricity, we will understand things much better. But the idea is that in an electromagnetic waves, which is a light wave, so light is an electromagnetic waves, but not all electromagnetic waves are light. So, for example, microwaves or X-rays are also electromagnetic waves, but not light. What's being transferred is really an electric field. Actually, an electric and a magnetic field. Now, I don't know if you guys remember what an electric field was, but the basic idea is that if I have two charges here, somehow the force of this guy is getting communicated to this guy. And the idea is that this guy creates something called a field around itself, so that when I put this other guy here, it instantly feels a force that tells it to go that way. So these fields, we can't really see them. Well, actually, we can, because like that's what light is made of. But like, they're like an invisible web, but we can actually modify them. So if I start moving these up and down, this guy eventually will move up and down because the field is being propagated. So there's a perturbation in the field that's being transmitted to this guy. So if I move this guy like this, then this guy is going to move like this, and so on. So an electromagnetic wave is nothing but a perturbation in the electric and magnetic fields. Now it turns out that, of course, this perturbation does not live in real space. This is just the intensity of the electric field. And therefore, in a sense, electromagnetic waves are transverse waves in the sense that the propagation is not parallel to the propagation. It really lives in a different world. It's an electric field going up and down. And that's all we need to know for now. Just bear in mind that the speed of light and of all electromagnetic waves is 3 times 10 to the 8 meters per second. And that happens every time unless traveling in a medium that's not air or vacuum. And we will talk about that later on in much more depth. Alright, now this is the last slide, and I know this was a long video, but most of the stuff you knew already. So we're going to talk about the different wave properties, and that's something that I made you do last year in the IGCSE. So this should be nothing new. First thing, we have the amplitude, and remember that the amplitude goes from here to here. So just like in an oscillation, actually, because a wave is just a bunch of oscillations happening all around a string, for example, there's an amplitude, and the definition is the same thing. So from the middle of the movement to the maximum, not the whole thing, just half of it. Then apart from this, there's a wavelength, and a wavelength is just the length of the wave. So remember that this is in space. So it's how much space there is between two consecutive crests or two consecutive troughs. Another way to see it is how long does the wave take to repeat itself? How long does a whole oscillation take to complete? So from here to here. So that's a wavelength too. And the wavelength is called lambda, and remember it's measured in meters because it's a length. Now, apart from the wavelength, we also have the period. And the period is, again, well, this thing is moving this way. So how long in time does it take for the next crest to appear? So when this moves this way, well, I was not, but yeah, so when this moves this way, how long does it take for the next crest to appear? And the period, again, is called t, and is measured in seconds, and so on. And then, of course, we have the frequency, which, just like in oscillations, is 1 over the period, and is measured in seconds to the minus 1, which are hertz. And the frequency tells us how many of these crests do we see every second. So if I'm sitting here on a chair, that's me counting oscillations, well, counting how many waves go through me, then the frequency is how many waves I see going past me in a second. And that's all we need to know. Now, the very last thing is a relationship between these quantities that will give us the wave speed. Now, of course, this wave is moving this way. Whoops. Yeah, actually, this way with a certain speed, right? So if I sit here I can measure the length from here to here, and if I know how long it took for this length to go past me, I can measure the speed of the wave, right? Because speed is distance over time. So the speed of the wave, v, is distance, which in this case it's the wavelength, over time, which in this case is the period, and I can use the fact that the frequency is 1 over the period to write that it's the wavelength times the frequency. And that gives us the wave equation that relates the wavelength and the frequency to the speed. And again, this can be deduced in a pinch, and also it's in your data booklet, so you shouldn't really, memorize this because it's obvious. And now we're done. So sorry for the long video. It was a lot of stuff, but I do think that most of it you already know. Okay, so here are the objectives again. Let's see if we have done everything we're supposed to do. This is straight from your syllabus. So if we can do this, we fulfill the syllabus requirements. So identify simple harmonic oscillations. Yes, it's when the acceleration is proportional to minus the displacement. Define period, frequency, amplitude, displacement, and phase difference. Yes, we did that. Say the conditions for simple harmonic motion. Yes, it's when the acceleration is proportional to minus the displacement. Qualitatively describe the energy changes taking place during one cycle of an oscillation. Yes, we did that. Sketch and interpret graphs of simple harmonic motion. Yes, we have. Define traveling waves. We just did that. Define wavelength, frequency, period, and wave speed. We just did that. Distinguish between transverse and longitudinal waves. We did that. Explain the motion of particles of a medium when a wave passes through it for both transverse and longitudinal cases. Remember, in one case they go like this, in one case they go like this. And they both actually do simple harmonic motion, now that you think of it. Sketch and interpret displacement, distance, and gradient for transverse and longitudinal waves. Well, we did this a little roughly, but we did that, and you will do this a lot more when you do the problems. And finally, solve problems. That's what you're going to be doing for the next 2 days. So good luck. Sorry for the long video, and I'll see you in class. Bye, guys.